will be presented by NEGAR. I need some help for your second name. Exactly. And she has a PhD in petroleum engineering, working on in situ combustion at Delft University. And now she's a postdoc researcher, again at Delft, working on in foam injection process, so enhanced oil recovery. Okay, we have 30 minutes.
Thank you. Good evening, ladies and gentlemen. Today I'm going to talk about the combustion for recovery of light oil at medium pressure. And this was my PhD work under supervision of Hans Browning and in scientific collaboration with Alexei, Mailybaev, and Marchesin. First, I will give a brief introduction about different mechanisms in petroleum industry. There, I will go specifically in air injection and try to explain a combustion mechanism. Then I will talk about our model, and at the end, some numerical results, different effects such as diffusion processes, effect of composition, initial watering present, and at the end, there will be some validation with experiment and then conclusion. As many of you know, there are three different recovery mechanisms in oil industry. The first one is primary recovery, which is a natural flow due to pressure difference between the reservoir and the production well. It can also sometimes include artificial lifts like pumps and gas lifts. This primary recovery can give a production recovery up to 30% to an oil reservoir. Then we have secondary recovery. It's more water flooding, and it can be sometimes water alternating gas flooding. It's also driving, the water is injected through the injection well and try to push the oil through the production well, and it's also sometimes used for pressure maintenance of the oil reservoir. Then we have tertiary recovery, which can give up to 15% of the oil recovery in an oil reservoir, which is composed of thermal, chemical, solvents, and other enhanced oil recovery. Our interest is in thermal, specifically in air injection. Why we are using combustion? This is the viscosity of the oil. This is the depth of the reservoir or pressure of the reservoir. If we go in higher pressures and higher viscosity oil, like oil sands or any other heavy oil, in-situ combustion will be an alternative. But in-situ combustion traditionally is a word for air injection into a heavy oil. What I'm going to focus on my presentation is an air injection into light oil because of the availability of everywhere rather than other gas injection like nitrogen and CO2, because then you minimize the separation cost. The advantage of air injection, it's applicable to highly heterogeneous low permeable reservoir due to heat production in air injection because of the oxidation. Well, I will come to it later. The fluid in the low permeable parts can be easily evaporated and then collected in high permeable part and then produced through the production well. It's also useful for different kinds of oil, heavy, medium, and any light oil. And the thing is that it combines effects of gas displacement with combustion recovery. This is a traditional picture of heavy oil, the in-situ combustion. It's the reservoir here, it's the injection well. Air is injected through this well, and we have horizontal production well here. When the air is injected here and then it's in contact with oil, it can start to ignite, or we can put it in ignition. And then we have the combustion wave here, or combustion front. What's left behind is, if it's heavy oil, it's some residue like coke or other stuff. If it's light oil, it should be clean, swept zone. Then in the front, it could be a steam region or any other flue gases coming out from combustion. And then we have an oil bank here, which is hot, and then cold heavy oil, and then it can drain to the horizontal production well and produce through the production well. It's believed that there are a couple of different reactions in the air injection phenomena. I will start with low temperature oxidation, which can occur between 150 to 350 degrees Celsius, but it depends on the nature of the oil. But the fuel is liquid oil, and hydrocarbon is reacting with oxygen, leading to oxygenated hydrocarbons such as alcohols, aldehydes, and other stuff. Then we have medium temperature oxidation, which can happen under this temperature, 400 degrees Celsius. It's the hydrocarbon formed from pyrolysis or even present initially in the reservoir. It combusts with oxygen and give us some carbon oxides and water. Then we have high temperature oxidation, which is typically for heavy oil reservoir. It happens in really high temperatures, and the fuel is normally solid coke, which is either cracked from the oil, or it can be also sometimes L2O reaction products, and then it also gives carbon oxides and water. If I want to show the difference between these mechanism for light oil and heavy oil, in the light oil L2O, low temperature oxidation is normally full hydrogen carbon bond breaking, while in the heavy oil it's more oxygenated, but production of oxygenated compounds which are not like favorable because they have high viscosity and they are really difficult to flow. And then M2O, which is typically for light oil, is small hydrocarbon oxidation. H2O can be negligible for light oil, but it can occur, but it has not really certain effect. And then for heavy oil, it's coke burning, generating carbon oxides and water. Then we have cracking and pyrolysis. In light oil, it can form smaller hydrocarbons, and in heavy oil, it's more coke, which is a fuel for high temperature oxidation reactions. And distillation, which play an important role in light oil reservoir, it can be negligible in heavy oil. And the focus of my work is to see the relative importance of evaporation and oxidation in light oil reservoir. Well, we started to think, well, the air injection at medium pressure, because what's normally in the literature you can find is high pressure air injection. They start in really higher pressures and really higher injection velocity. And we said that it could be applicable for efficient light oil recovery. And then the interaction between the combustion and vaporization is the primary mechanism in M2O, whereas in H2O combustion, it's not. H2O process, combustion is more important. We also showed that relatively small amounts of light oil increase the recovery efficiency, and water vaporization and condensation has a positive effect on the light oil recovery in an air injection. And also we believe that physical chemical sorption can take place before any M2O mechanism in a light oil reservoir. We had a model is composed of conservation law. Well, for our components, we had 3 components in gas phase: oxygen, hydrocarbon gases, which is a vaporized hydrocarbon in gas phase, and remaining, which consists of other carbon oxides and nitrogen, and also water in a gas phase. And then we have, in one case, we have one component oil, light oil. The other one, we had a 2-component oil, light and medium component. And then we have our energy balance, thermodynamic relationship for liquid hydrocarbon and vaporized hydrocarbon, and then constitutive relation. We use Darcy law here. We assume a 1D domain. Air is injecting from the left, and we are producing everything from the right-hand side. We had 2 reactions, one for light oil, one for medium oil. In 2-component system, light oil can both vaporize and combust, while the medium hydrocarbon can only combust. This is the oil mass balance for 2 component, medium component and oil component. accumulation, convection, and then we have a reaction source term for medium and reaction for the light hydrocarbon, and we have vaporization only for light hydrocarbon. And then we have gaseous hydrocarbon, which is when the source term is vaporization, oxygen, which is acting in both reactions, and then we have remaining gas. And we have Arrhenius-based reaction type. And this is the energy balance, accumulation, convection, and we have conduction and source terms, which is a heat of reaction and heat of vaporization. This is the typical wave sequence of this problem. It's based on analytic study. If you look at here, you can see that there are 3 different thermal waves occurring here. This is the thermal wave, 3 different waves happening here. This is the thermal wave, M2O wave, and saturation wave. Thermal wave is started from the injection or initial value. We put the initial temperature as injection temperature and goes up, and then reach to a plateau before just upstream of the M2O wave. And this M2O wave, as you can see, can be the reduction in the oxygen fraction can be indication of any combustion happening here, and also an M2O wave. And then downstream of the M2O wave, we have typical Buckley-Leverett refraction, shock, and initial value of a saturation wave. If we look more in the M2O wave, we can see 2 regions, which is vaporization region and reaction region. In the analytical solution, it was assumed that the vaporization region is really fast. That's why you see really, thin vaporization region than reaction region. In vaporization region, we assume the temperature is constant, and there are small amounts of oxygen because there's no oil is left behind, and there's no oxygen consumption, and we have almost constant oxygen. Then it starts to be consumed while we have also this YH, which is gaseous hydrocarbon, start to vaporize and then condense due to the temperature changes downstream of the combustion wave. Then we did some numerical stuff and include the diffusive processes like mass diffusion, capillary, and thermal diffusion. Then we add another component to the system to see the effect of medium component fraction, and then we include the initial water and the water as a reaction product. This is the numerical solution for one component oil. Well, you see the similarity qualitatively between the numerical solution and the analytical solution. The only difference could be this temperature wave, because in the analytical solution there was no conduction, heat conduction, but in a numerical solution we put heat conduction. This behavior can be an indication of heat conduction. And then we have a smoother oxygen reduction due to, and also a smoother gaseous hydrocarbon increase due to adding diffusion to the system. Then we did the simulation with a smaller gas diffusion, I think 100 times smaller. We see almost the same behavior. The only changes was the temperature and this sharp reduction in oxygen profile. And then we did it with high gas diffusion. We end up with lower temperature, spike here, and then completely diffuse a process of oxygen reduction, which is widened, and also the hydrocarbon gases, this one, which also a bit, it's not sharp anymore. Then we did it with the small capillary diffusion. Well, I would say that the whole process was a bit smaller, but still the structure of the wave were preserved. And then we did it with high capillary diffusion. Well, actually not realistically high. It's really high because we want to see the difference. But as you can see, that's completely different process, and no oil is already here. Most of the oil is swept away by gas injection phenomena, and the small amount of oil which is left behind start to react with the oxygen, and the M2O wave velocity is really slow. That's why it leads to higher temperature upstream of the M2O wave. Then we decrease the thermal conduction. As you can see, we almost get the qualitatively same behavior as analytical method, because in analytical the thermal conduction was 0. And then we did it with extremely high thermal conduction for rock. And then we see completely all the profiles are more wide, and it's happening in a bigger area, like temperature increase, or even this condensation of the gaseous hydrocarbon. Then what we did, we add another component as medium oil, and we only let the medium component to combust but not vaporize. This is a numerical simulation results of the 20% of medium component in, and then 80% is light component. As you can see, again, the structure is the same. We have a heat wave, we have combustion wave, and this is the saturation of the oil. This saturation is because of the M2O wave. Then we have light component and heavier component. But still, small amounts of heavy oil is left behind. It's because of the initialization effect, because at the initial times, the M2O wave is not still so, let's say, efficient to be able to move the whole oil downstream. Then we increase the amount of medium component to 60%, and then we still see the same behavior. The only thing is that we have more oil left behind, which you can see slightly decreased in oxygen fraction, which leads to a bit decrease in the temperature. But at the end, light oil was responsible for the whole recovery mechanism, and it can push the heavy oil through the reservoir and production well. But then we increase the medium component to 80%, and we see completely different mechanism. We cannot name it M2O anymore. It's more like high temperature oxidation, which is happening in heavy reservoirs. You see that the light oil is completely responsible for vaporization, condensation, and it's happening. Everything is happening completely downstream of the combustion wave, while heavy oil is responsible for the combustion, and they are acting completely separate with each other. And because we don't have any vaporization, any heat consumer effect here, only combustion, which is a heat production, we have higher temperature, which can be as high as high temperature oxidation effect. These two minima here, this one could be due to the combustion of the heavy oil, then the other one could be due to the vaporization of light oil. And then we did some other simulation. We add water. Well, water was actually in. We consider the condensation of produced water as a reaction product. Oops. Here is our numerical for one component with no water condensation. Here with water condensation, you see this orange curve, which is a steam fraction in gas phase. The condensation of it leads to these dots, small amounts of water saturation, and then this whole stuff, like adding water condensation, speed up the recovery. Even it's so small, and we did a mass balance, and it's this water condensation only responsible for 10%. If you have water initially in the reservoir, this water is only 10% of the whole water, but still it can enhance your oil recovery, and it can fasten your recovery. Then we add an initial value with heptane. Heptane has boiling temperature almost around water, close to water, a bit higher, but it's close to water. And then we see completely different behavior. We still have temperature thermal wave, combustion M2O wave, and we have saturation wave, which is moved to the right. It's not possible to see it here because it's possible to see it initial times. And then we have vaporization of water, and then we have buildup of steam, and then we have buildup water bank, and then it goes to its initial value, while we also have the first oil bank, which is due to the M2O wave, and the second oil bank could be because of the water bank just behind the oil bank. And again, if we compare this one with our base case, we see that water has a positive effect on the oil recovery. Then we did it with Dotican, which is a more heavier component, and it has a really higher boiling temperature than water. We see completely different behavior. In this case, if you see the condensation of water and oil is happening together, while vaporization of the water is always upstream of the combustion wave, while here water and oil is completely separate from each other. This is vaporization, condensation of oil. This is vaporization and condensation of water. And water is always downstream of the M2O wave, which means that it's not having that positive effect on the oil recovery because it's not acting as a pushing mechanism to the oil. And also this purple one is oil saturation, the saturation wave, and then we have a water saturation, and then it goes to its initial value. Then we add a high water saturation, 60%, the other one has 20%. We see the same behavior, completely different vaporization and condensation of water and oil, and the whole process is really slower than the other one because water is more volatile in this system, and if you put more water in, then the wave needs to be weight there to be able to vaporize whole water, and then the whole process is slower. Then we did the same 60% of water in heptane water, and we saw that it still has a positive effect, and it can fasten the whole recovery mechanism. And we are seeing still the same behavior of water vaporization happening upstream of the M2O wave, and then condensation of both at the same time, which causes the recovery to be more efficient. And then we draw the produced oil over the initial oil with time. The left one is for heptane. This is when we don't consider the condensation of water. You can see that it can give almost 20% underestimation of oil recovery. It can show the importance of water in the reservoir or water condensation. This is with initial water of 0. The green is with 20%, and the purple is 60%. As you see, when the oil boiling temperatures around water or close to water, the increase of initial water saturation can lead to higher production. You see 3 different stages. The first stage is due to the completely gas injection effect. When you pressurize the whole system, you put gas, immediately you have a rapid production. Then you have 2 other systems. M2O is more responsible for these 2 reactions. I will come to it later. And then this is for Dotican. This is for 0 water saturation, and this is for 20%. If I put 60% of water saturation in Dotican, which is with really higher boiling point rather than water, then you see that higher water saturation has a negative impact on the oil recovery. If I look at the heptane water mixture profile, it's in the initial times. This is this profile, which is the saturation wave, which was not possible to see in other figures, which is happening in initial times, is responsible for this part. And this wave, which is happening here, it's in intermediate times. Oh, it's this one. And if I want to go back, this wave, which is happening at the later stage or almost end stage, is this stage, which gives us this recovery profile. And then we try to validate the whole process with experiment, which was the most challenging and difficult part of my PhD. We had a reactor. We put a core in and tried to saturate it completely with one component, oil, which was hexadecane. It started to inject, well, under pressure. The pressure we used was 10, 30, 50, and 70 bar. We start to inject oxygen at a constant, air at a constant temperature from bottom and produce everything from down. We had a separator which can separate the oil and gas, and the gas portion of the gas went to the gas chromatograph, and then the component in the gas was able to be analyzed. The reaction model was proposed was this hexadecane, which can react with oxygen and can give us some oxygen addition products. And this oxygen addition product can be then converted to hexadecane itself, or further undergo some more oxidation. And if this Q hat in this reaction model is bigger than Q, it gives the absorption of oxygen and formation of oxygen hydrocarbon. But if the Q hat is smaller than Q, it gives a desorption or release of oxygen by physical or chemical phenomena. Well, I won't go through the whole experiment here. I only give two of them. We did air injection into a core filled with hexadecane at 20 milliliter per minute, if I remember right. It's 30 bar experiment. And as you can see, we start to heat up the whole system with 10 degrees Celsius per 10 minutes. And then starts to see that the deviation of temperature which can be an indication of heat releasing by reaction. And then we have these peaks, which are indication of combustion happening here. And then this is the analysis of our effluent gas, oxygen reduction here, almost here. And then we have nitrogen. We have a peak of nitrogen here. Well, nitrogen should be neutral. And then we had CO2, CO, which you can see it. CO, you can see it from this side, and CO2, nitrogen, oxygen from this side. And you have a couple of small ethylene, ethane, and cracking products. And then we calculate oxygen over nitrogen. For the first times, it's constant, which is in the amount of oxygen over nitrogen in the air. Then it goes down, which is almost here, which means that oxygen is sucking by the oil, or it's either physically or chemically is binding with the oil. Then after a while, it starts to release the oxygen, but then it goes to a plateau, but then it starts to release more oxygen, which shows us that there could be some physically dissolved oxygen in the oil, which are released later. And then with that reaction model, I showed you that any hexadecane here is converting to this oxygen addition compounds, and later they are either consuming by reaction, or which is this curve, or again releasing oxygen and converting to hexadecane. And this was the same experiment, but with higher injection rate. You see still small peaks here, which are indication of a reaction. But the thing is that when we inject in with higher injection rate, we give less resident time for oxygen to be in contact with oil, and we have a bit oxygen breakthrough here while we were expecting to be zero. But finally, because we were we were heating up the whole system. The temperature was high enough to capture the oxygen there, and then we have oxygen 0 here, and at the same time releasing of CO2 and CO, and the same behavior here. If we look at our different experiment, we almost see the same behavior of the oxygen release from the oxygenated hydrocarbon in different stages. They are for different pressures, 10, 30, 45, and 70 bar experiment. And we draw the oil recovery versus time. We again see the same 3-stage recovery. This is due to the pressurization of the whole system, like gas injection, then the intermediate system, intermediate oil recovery stage, and this, which is most important one for us because it's completely, they all start when the combustion peaks are starting in our experiment, which is the indication of M2O recovery. You can see the higher the pressure, the higher the oil recovery. We also calculated combusted oil over oil recovered with pressure, and then combusted oil is proportional to the amount of oxygen we are putting in the system, and oil recovery is partly liquid oil, which is pushing by the M2O and also gas, and the partly is the hydrocarbon, which is vaporized in the system. And we see this minimum, which indicates that the more oil is combusted in 30 bar, and it can, to give a rough idea of how much oil we are combusting in a reservoir while we are putting air in, it's almost between 0.02 to 0.18 of the whole oil, which can be combusted through the combustion mechanism. Well, if I have time to go to conclusion. Well, we showed that the M2O medium temperature oxidation is a promising method to improve the oil recovery. Then we also showed that if we have a small amounts of, we showed that the M2O displays the oil at the expense of small amounts of burned oil, and the solution consists of thermal wave, M2O wave, and saturation wave in one component oil. And the order between vaporization and oxidation in the M2O wave changes with different sets of conditions. Then for a predominant light mixture, vaporization occurs on the upstream of the combustion, and then the combustion front velocity is high as less oil remains behind in the combustion region. But for oil with more non-volatile components, the vaporization moves to the downstream of the combustion zone, and more oil is left behind. Therefore, the combustion velocity is slower. We get to really high temperatures, almost around high temperature oxidation zone. And then it can show us a bifurcation point in the composition of the oil, which can change the character of combustion process from a vaporization dominated to the combustion dominated process. The model and also experiments give almost between 82 to 90% of the oil recovery opposed to 60 to 70% of the water displacement. And we also showed that the burning over the produced oil can be changed from 2% at 10 bar to 18 at 30 bar, and then decrease to 5 in higher pressures. And we also showed that the boiling point of the oil, if it's close to water or slightly higher, the water can have a positive effect on the recovery of the oil. Higher the water saturation will be more beneficial. But if you have a boiling temperature really higher that temperature, then water won't have a positive effect on your system, and then it will slower your whole recovery mechanism. Oh yeah, we also, this was more our idea, that we showed that this oxygen adsorption step takes place at low temperature in the initial before the combustion. And these oxygen compounds then release the oxygen at higher temperature, either to be converted to hexadecane, or they also undergo the combustion reaction furthermore. And I think I will skip it. Thank you very much.
Yes, thanks for a nice presentation.